Hello everyone, my name is Luke Hanks and this is my Lab 3 video for Physics 2211. So this is the black hole lab, and basically the purpose of this lab was to explore how forces and momentum in basically any vector can be broken into parallel and perpendicular components, and we did that by coding a simulation of a star and black hole system, and we use the resulting force components to determine the mass of the black hole at the center of the system. So the principles we use here are Newton's universal law of gravitation, and then you can see how the rate of change of momentum and the net force are broken into their perpendicular and parallel components. And then over to the right, you see how the the parallel and perpendicular components of the rate of change of momentum are defined. So let's move on. Here's my data from my lab. The three pictures are just three pictures I decided to include. And as you can see, there are three force vectors. The orange one is the net force, the light blue is the perpendicular component of the force, and the purple one is the parallel component of the force. So my values for those are on the screen, but the net force is 8.47 times 10 to the 28th newtons. My parallel component of the net force was 3.68 times 10 to the 27th newtons, and my perpendicular component of the net force was 8.46 times 10 to the 28th newtons. The mass of the black hole that I determined was 1.24 times 10 to the 34 kilograms. And one way I think I could have improved my mass estimation here was by averaging all of the values, because the way that the lab works is that it calculates the mass of the black hole for each time step. But so my final mass that I have right there is actually just the calculated mass at the final time step. But if I wanted more accurate, I could have averaged all of the intermediate values, but I was not sure how to do that in GlowScript because I'm not familiar with coding. So speaking of coding, here we go. I had to change the mass of the star to be 2.0 times 10 to the 30th kilograms, and I had to change delta T to be 86,400, which is just the number of seconds in a day. So here's my second coding slide. I had to change the initial and final momentum vectors to be the initial velocity and final velocity times the mass of the star, respectively. And then delta V and delta P are just the final minus initial for their respective vectors, and then dP dt, which changed to be delta P over delta T. Fnet was dP over dt, and I had to change P hat to be the initial momentum over the magnitude of the initial momentum, and then the the magnitude of P over dt is going to be the magnitude of the final momentum minus the magnitude of the initial momentum all over delta T. So here we go, coding part 3. I had to change the dP dt parallel to be P hat times the d magnitude P dt. I changed the net force in the parallel component to be dP dt parallel, and I had to change dP dt perpendicular to be dP dt minus dP dt parallel. The net force in the perpendicular direction is just the dP dt in the perpendicular direction. So finally, I changed the mass of the black hole to be magnitude of the net force times the magnitude of the star's position squared all over the g constant times the mass of the star. And this is just a rearrangement of Newton's universal law of gravitation. Here's my fourth coding slide. I had to change the arrow scale to be 1 times 10 to the negative 17. And then I just changed the position for each of the arrows to be the star position, just so they would line up. And finally, I changed the axis for the net force to be, for the first arrow to be net force times arrow scale. And then the second arrow was just the net force in the parallel direction times arrow scale. And then the third arrow was just the net force in the perpendicular direction times arrow scale as well. So what does it mean? In your analysis, you should discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. So, as we know, as we've learned, the net force is equal to the rate of change of momentum mathematically, but they have one pretty important difference, and is that the force, the components of the force are what's causing the motion, and the rate of change of momentum is what's resulting from the force. So the distinction here is that the net force is causing the motion, and the change in momentum is a result of the action by the force. And then what if? Imagine the black hole whose mass you found was removed, and a different black hole is placed in the same location. Assume the motion of the observed star remains unchanged, and it's affected only by the gravitational force of the new black hole. Could you tell the difference? AKA, can you find a value of the mass of the new black hole that is different from the original? And the answer is you could not, because If the motion of the star remains unchanged, that means that the mass has not changed at all, because the motion is determined by the net force, and the only force that we have involved here is the gravitational force from the black hole. So if the motion remains unchanged, that means the force remains unchanged and the mass remains unchanged. And that is all. Thank you for listening.